and welcome to another WJEC A-level physics question. This is from January 2014's Unit 1 and it was question 7, which is a sort of a work energy and power type question. The first part of the question talks about wind turbines being used to generate electrical energy, and the way that they do that is they convert as much as possible of the kinetic energy of the air that enters them into electrical energy. So what we've got is a diagram showing a wind turbine, and it's showing a cylinder of air entering that wind turbine, moving at a speed of u, a fairly high speed of u, and coming out of the other side at a reduced wind speed of v. Now the volume of air arriving on the blades per second is AU. That's simply the volume of the cylinder. The cross-sectional area of the cylinder is A, and in 1 second, which is what we're talking about here, the length of that cylinder will be U meters. Remember that U meters per second literally means a distance travelled of U meters in 1 second. We've got to show that the kinetic energy per second, or the power arriving into that wind turbine, is given by P equals 1/2 A rho U cubed. Well, kinetic energy is half mv squared, so we're going to be using that. Here, the mass is going to be the volume times the density. And the volume, we've already told, is AU, so the density is rho. And V is going to be the speed that the wind is entering the air. Is entering the turbine. In other words, it's going to be U. So our kinetic energy formula, or our power, which is kinetic energy per second, is going to be 1/2 A times U times rho times U squared, which will indeed give us the 1/2 A rho U cubed that we were asked to give, the U times the U squared giving U cubed. The next part of the question is a proportionality question, and it tells us that the power arriving is proportional to the square of the radius, because the area depends on pi r squared. So doubling the length of the wind turbines, or the turbine blades rather, will increase the power arriving by a factor of 2 squared. If we double r, double the radius, we got a square factor here, and 2 squared is simply 4. So doubling the radius will give us 4 times the power. Doubling the wind speed, well, if we look at the equation that we've got up here, the power is proportional to the speed cubed. So if we double the wind speed, we're going to get 2 cubed, or 8 times the power from this wind turbine. The question continues by pointing out that we can't remove all of the energy arriving from the wind, because the wind will still be moving when it leaves the wind turbine. And it gives us an expression for the power possessed by the moving air once it's left the turbine of P is equal to 1/2 A rho V cubed. So using that one and the one that we derived earlier, we've got to write an equation for the power lost by the air as it passes through the turbine. So I'm going to call it delta P. And it's going to be the difference between the input power, 1/2 A rho U cubed, and the output power, 1/2 A rho V cubed. Now we could simplify that by doing a little bit of factorising. If we factorise out 1/2 A and rho, then we've got U cubed minus V cubed. Suggests why it's not a good idea to erect wind turbines short distances behind each other. Well, the wind speed has been reduced once it's left the turbine, so that means that there's less power being delivered into the next turbine. So if we just say something like each subsequent turbine will have less input wind power. You'll usually see when turbines are built on mountains, they're well apart from each other. Now we're told that we've got a particular wind turbine with blades of length 2 meters, wind speed enters at 7 meters per second and it leaves at 5 meters per second. And after passing through the turbine blades, we've got to find the net input power to the wind turbine. Well, the input power to the wind turbine is going to be the power lost by the wind, and then that power lost by the wind will be converted into electrical energy with a loss due to inefficiencies by that wind turbine. So all we're going to use is the equation that we derived in part 3. So we're going to put in the figures. The area is pi r squared, r is 2 meters, the density is 1.2, and then we've got 7 cubed, take away 5 cubed. So let's put that into the calculator. And that will give us about 1640 watts. Might be useful to store that in a memory, but I think we can get away with an answer button. The question continues by giving us a graph of the efficiency of the wind turbine at different speeds. And we'll notice here on the graph that there is zero efficiency at any speed here less than 4 meters per second. And the question asks us why that is. Well, wind speeds of less than 4 meters per second aren't going to be fast enough to be able to turn the turbines to be able to overcome friction. So just say something like the wind doesn't provide a big enough force to overcome friction. Then we've got to use the graph to determine the actual power generated by the turbine in A part 5 with a wind speed of 7 meters per second. So if we carefully read 7 meters per second off the graph, we'll find that that efficiency is about 54%. So all we're going to do is find 54%. Let's call it P out if you like. It's 54%. 54 over 100 or 0.54 of that 1640 that we worked out just now, and using the accurate figure we get 888 watts. Finally, the question asks us to state why an undersea turbine of the same size as the wind turbine in A5, when placed in a water current of speed 7 meters per second, would provide significantly greater power output than the wind turbine. Well, if you remember in the formula, we've got that term with the density, and the density of water is close to 1,000 times bigger than the density of air. So all we're looking for here is simply that the density of water is greater than, or very much greater than, the density of air. I'd personally put in the very much greater than because of that word significantly in the question. Thank you for listening. Please remember to like and subscribe, and if you have any questions, add them in comments to this video. Goodbye.